Hi, this is the final presentation for ME555 Design Optimization. We're Group 5. This slide introduced the overall system and its three subsystems. The system we're optimizing is a solar panel system, and our objective is to minimize the cost per kilowatt hour over the panel's full operation life. To do this, we divide the subsystem into three subsystems. Subsystem 1 is panel design, where we aim to minimize the square meter cost per kilowatt hour by selecting optimal cell types, packaging, and efficiency. Subsystem 2 is manufacturing and automation, which focuses on minimizing the cost per area or dollar per feet square by balancing panel size, production volume, and automation level. Finally, subsystem 3 is development and maintenance, where we minimize the total cost per unit of energy by optimizing rooftop layout and cleaning strategy over a 25-year lifetime. Together, these three subsystems form a complete lifecycle optimization approach for solar energy systems. This slide shows the system flow diagram, which captures the full lifecycle of a solar panel system from design to manufacturing and deployment. Each subsystem shares key outputs with the next, forming a coupled structure. For example, panel specification from the design phase become input for manufacturing, and the physical panel dimension and cost flow into the deployment model. The system's input includes solar panel characteristic, production parameters, and installation constraints, while the final output is the cost per kilowatt hour. The system boundary is defined by the start of panel design and ends after 25 years of energy operation. This diagram highlights the coupling between subsystems. First, subsystem 1 passes material cost to subsystem 2, where manufacturability constraints can limit cost-effective designs. Second, it also sends power output and lifespan data to subsystem 3. Finally, there's bidirectional coupling between subsystems 2 and 3. Deployment constraints like panel size and quantity can feedback and restrict manufacturing choices. We chose a system-level approach because the subsystem, design, manufacturing, and deployment are non-linearly coupled. Decisions in one directly affect the cost and feasibility of the others, so optimizing them separately leads to suboptimal results. A system-level formulation allows holistic cost minimization while ensuring that designs are feasible, manufacturable, and deployable. In our solar panel project, coordinating trade-offs like panel size affecting layout and cost led us to best solution. In this project, we chose IDF formulation because our three subsystems are strongly coupled. Traditional approaches like MDF require solving all coupling variables at every iteration, which is computationally expensive and often unstable under strong coupling. In contrast, IDF introduces auxiliary variable to decouple the feedback loop, allowing us to preserve each subsystem's internal structure while maintaining consistency across shared variable like panel dimension, material cost, and power output. This made IDF the most robust and efficient method for our solar panel system.
Our objective is to minimize the total cost per kilowatt hour over the system's lifetime by optimizing across three subsystems. We apply a system-level optimization using the IDF method, which lets us preserve each subsystem's internal model while enforcing coupling constraints. These constraints link variables like material cost, panel dimensions, and power output, ensuring consistency across the systems. Each subsystem has its own cost-based objectives, and the final system objective is summation of these three. In subsystem 1, we restrict material cost to under 300 per square meter, require a minimum lifespan of 180,000 hours, and keep the electronic efficiency coefficient between 0.5 to 0.98. For subsystem 2, we include a manufacturing budget limit requiring a minimum level of optimization and enforce bounds on panel area and number of panels to ensure scalability and cost efficiency. In subsystem 3, the deployment model must meet geometric and operational constraints. The roof must fit the parking layout, support at least 500 parking spots, and stay within a maximum area of 10,000 square meters. For system-level trade-offs, we balance high efficiency with cost. Better material boosts energy yield, but drive up both material and manufacturing expenses. Next, we trade off panel size and layout flexibility. Larger panels are efficient to wire and install, but harder to fit on complex rooftops and cost more to produce. With automation, higher level reduces labor costs but only pay off at larger scales due to high capital investments. And the cleaning frequency improves energy performance but increases long-term maintenance cost, especially for larger rooftop systems. We also deal with structural trade-offs. Multi-floor parking maximizes roof space, but introduces stricter spatial and layout constraints. Finally, pushing for longer lifespans improves cost effectiveness over time, but narrows the set of feasible materials and design configurations that meet all the constraints. First, the linking variables like material cost, power output, panel dimensions, and number of panels form the backbone of our coupling across subsystems. These were previously treated as fixed parameters, but in our system-level model, they are joint optimized and enforced via constraints. Second, compared to the individual subsystem models, the system model allows for shared variables, bidirectional interactions, and global optimization, leading to a better trade-off handling and overall performance.
In our model, the total material cost CM is the sum of the cell cost, the top layer cost, and an additional term that accounts for electronic efficiency. This last term uses a natural logarithm to simulate the diminishing returns of higher efficiency. For lifespan, we assume a base of 250,000 hours, or about 28.5 years. The total lifespan is adjusted by the chosen cell and top layer types as well as electronic efficiency. Notably, higher electronic efficiency leads to greater stress on the system, which slightly reduces overall lifespan. Our optimization method uses a hybrid approach. First, we run a genetic algorithm in MATLAB to explore the global search space. This helps us to handle complex, nonlinear problems and avoid getting stuck in local minima. Next, we use fmincon to refine the result. Starting from the genetic algorithm's output, fmincon performs a local search to fine-tune the solution and reach a nearby minimum with higher precision.
This slide shows the optimization results for our solar panel system across 5 independent runs. At the top, we summarize the best performing solution, which achieved the system cost of just $0.0035 per kilowatt hours. This solution used cell type 2 and top layer 2 in subsystem 1 with a high electronic efficiency of 95.63%. In subsystem 2, the configuration required around 1,111 panels, each with an area of 9 square meters, and used full automation. For subsystem 3, we used the rooftop layout of approximately 200 by 50 meters, with a 5-floor parking and a typical panel size of 3 by 3 meters. The table at the bottom compares all 5 optimization runs. While each run uses different initial guesses, the resulting objective value remained low and consistent, ranging from 0.0035 to 0.0041. This shows the optimization was stable and converged to a robust solution. This slide highlights a few key discrepancies we observed across the 5 optimization runs. First, in run 5, we found that even though the objective value was low, the solution violated the coupling constraint. This shows how small mismatches between manufacturing and deployment panel areas can make an otherwise promising design infeasibility. Across the board, subsystem 1 and 2 show slight variation in design variable, which actually demonstrated the flexibility of the system. It means multiple design paths can achieve similar optimal performance. In contrast, subsystem 3 variable remain more constant, particularly panel size and roof dimension. This makes sense since these values are tightly constrained by layout feasibility and throughput requirements. Overall, the results suggest that while the system is flexible in some areas, certain constraints like coupling and layout are critical and must be satisfied precisely.
After we have gained the optimal value for our subsystem, we now do the post-optimality sensitivity analysis here. We first do the constraint sensitivity analysis on roof length and number of floors, because those two are the only constraints that are activated. So we first do the sensitivity analysis on roof length. The constraint value before we change it is 200 meters, and then the optimal result is 0.0035. Then we tried different constraints with 180 and 220, and we also obtained the optimal results here. So based on the equation here, the sensitivity coefficient for roof length is 0.000325. Then we also did this again for the number of floors here. Because the number of floor is integer, so we plus and minus 1 here. The original value is 5 floors. And then we tried with 4 and 6 floors here. And based on our equation, the sensitivity coefficient for number of floor is 0.00045. So in conclusion, the constraint of number of floor is more sensitive. So now we do the sensitivity analysis here. We have chosen the material cost, the labor cost, and also the cleaning cost as the parameters to analyze because they are the main cost contributors in each subsystem. So for the material cost, we use plus and minus 10 to alter the parameter values. And for the labor cost and cleaning cost, we use plus and minus 10%. And the optimization result here is also shown here in the table. And the sensitivity for each parameter is also shown on the right. We use the equation on the left here to compute the results here. So based on the results we have here, it seems that the labor cost is the most sensitive to our system optimization. The sensitivity of it is 0.0052.
Here we take a final look at our results. When comparing each subsystem by itself versus an integrated approach, we see a clear advantage in system-level optimization. Subsystem 1's power output saw an increase, while Subsystem 2's cost per area dropped slightly, and Subsystem 3's cost per kilowatt hour saw a substantial decrease. However, our reality check reminds us that real-world solar system typically costs around 6 cents per kilowatt hour. This discrepancy likely results from overestimating energy production, underestimating certain costs, and assuming optimistic parameters. Looking ahead, we plan to refine our engineering assumptions, especially regarding energy yields and true project expenses, and explore other optimization methods. These efforts will help align our model more closely with practical solar deployment, ensuring accurate forecasts and even further cost reductions in the future.